Okay, this is supposedly video 16. I know there were some other videos in there, but you've made it this far. Yay! So we're going to talk about Gershgorin's circle theorem and power method. Gershgorin's circle theorem allows us to use a quick trick to estimate eigenvalues for a matrix. So you want to estimate eigenvalues for a matrix. Okay, so this is pretty cool. At least I think so. Let's say you have, I'm just starting with a crazy matrix, I, 1, 0, 2, 1, I, 3, minus 4, 10. Okay, so the first row tells us that if I put a circle, a center is equal to I, and radius is the magnitude of all the other pieces added up, then I should find an eigenvalue for M. So if I draw my complex plane here, right, and I'm going to put my center here, my radius of 1, then I should have an eigenvalue there. Well, let's look at the next row. Let's see, this, and I'm going to go down the diagonal. So each diagonal element is going to trace out the center of something interesting. Okay, so this would be 1 instead of I. And the magnitude, so I'm going to have a center is at 1 in the complex plane, and the radius is 2 plus 1 because I take the magnitude of each of those, so a radius of 3. So this is going to be a little bit larger, something like that, and I'm going to have lambda somewhere in here. Well, you see they're overlapping a bit. A lot. Okay. And then the last center is at 10, and the radius is equal to 7. Okay, so that's a little harder to draw, so I'm going to try shrinking this guy down. Let's see if I can put this over here. What would it look like at the center of 10 and a radius of 7? Well, I don't know. I'm going to go with this. Let's see, 10 is over here. Radius is going to be something like that. Okay, it's going to be another lambda over here. So there's some overlap region between the green and the blue circle, but essentially what you get is 1 lambda per circle. Okay, typos aside, I've got M in here. Let's just double check that it's doing what I expected. The first component should be I. Notice I'm using my hack that I showed you before for I, because if I try to put the square root of -1 in there, it'll just choke on me, so I have to make my own copy of I, which is J, ironically. And so this piece is actually 0 plus I, and then 1, and then 0, and then 2, 1, I, 3 minus 4, and this one is 10, right? So actually it's 1 times 10 to the power of 1. So we're good to go. That looks like M to me. So then what I'm going to do is I'm going to ask for eigenvalues in eigenvectors. Okay, are we ready? I have eigenvectors in there too, but all I'm worried about right now is trying to figure out where my eigenvalues are. And it's saying that there's one with a pretty considerable, well, they all have some imaginary component. How about that? So I have one that's at roughly -1 and almost 1 in the I direction. So it very well may be my red one, but maybe it's not. So I have one something like that. There's one somewhere like that. It could, it's not clear which circle gives rise to which eigenvalue. Well, let's look at the next one. The next one is roughly 2 and then half an I. So roughly 2 and then half an I. So it could be like here. It could be in the green circle or the blue circle. I'm not really exactly sure. Oh wait, it's got to be lower down here. I drew it too high. Sorry. This isn't perfect. Okay, where's the third one supposedly? It's at 10 and then negative a half. So I'm way out here. So that third one, that third eigenvalue that was listed, it has to be from the third row here, this one that I'm calling the blue eigenvalue. Okay, so that one is at about 10 and then minus I over 5. That's just roughly, that's not exact. The other one, okay, so this one has to be from the green circle because it can't be in the red circle, so the last one has to be in the red circle. Sometimes you can't actually reverse engineer what goes where. This is about 1.98 plus about 0.54I, and then the blue one, sorry, the red one. So this guy is the one that's about, let's say, -1 plus 0.88I. Okay, so you basically, each circle gives you one eigenvalue, but you can't always pigeonhole them. In this case, we were able to because we could figure out where the blue one was coming from, and then we could figure out where the green one was coming from, and then we could figure out where the red one was coming from. But sometimes they overlap in such a way that you really can't untangle it without digging deeper. Okay? You can probably also Google the official statement of this theorem, but every time I've seen an official statement of this theorem, it looks way more confusing than just drawing circles and saying you have an eigenvalue inside each circle. Because they'll say something like something about the union of circles and blah blah blah, and it's like, okay, whatever. I think you understand. You basically can't wander out of your circle. Okay, so I'm going to let you play with that on the homework, and now we're going to talk about the power method. Yay! Just like Gershgorin, I'm going to give you an example rather than a formal explanation. I'm going to start with a matrix that we would like to find an eigenvalue eigenvector pair for. And what we will do is we'll find the dominant eigenvalue. So we will find the dominant eigenvalue eigenvector pair. There are other similar processes that are a little more refined, but this is just kind of finding the biggest magnitude one. No ties. We're going to presume there's only one. That's not necessarily true, but for this demo, it's going to be true. You need a starting vector. So like your recipe, you need starting vector, and you need a matrix, and then you keep pushing the vector through the matrix, rescale, repeat, and we see where it levels off. So in your homework it's going to say do 3 of these and see where it stops. So you're not going to just go until you get to a certain accuracy. You're just going to do like 3 iterations and then say what you got. Alright, so for this example, okay, so we have a matrix and a vector as required. And now we're going to head over to Python and work on this. We already have NumPy in there. We just have to pick another M. So I'm going to type this in. Say -5, 13, 0, -1, 0, 2. Okay, and we have a starting vector. Presuming there's only one dominant eigenvector pair, it doesn't actually matter much where you start. I guess if you started exactly orthogonal to, like, there may be one direction in which if you start, you can, yeah, I don't know, like, if you stay exactly on another eigenvector, then you won't find the dominant one, but it's so unlikely that that's going to happen. Okay, so I'm going to do the following. V0 is going to be B, and then V1 is going to be M times, because I can multiply this way, which is crazy, but I can do that. What do I get? I get 10, 8, 1. So what was B originally? It was 1, 1, 1, and now I get 10, 8, 1. So we're going to do some kind of scaling here, and there's different ways you can scale, but what we're going to be doing for this procedure is we're going to be scaling by the maximum of the absolute value for the resultant vector. So I'm going to scale by 10, right? So V1 is equal to V1 divided by 10, so that the maximum component will always be 1. Okay? Okay, that was fun. Let's do it again. V2 is M times, the at sign is a times, V1. What is V2? V2 is V2 divided by max abs V2. So again, V will stabilize, and all this will stabilize. But let's go ahead, and this is not what's going to happen on your homework. On your homework, you're just going to do a few iterations and stop. But it's too fun not to do this now. Okay, so V equals V2. I'm going to just call it V generically for I in range, I don't care what. V equals M times V. Okay, and then what I'm going to do is I'm going to print max abs V, and then I'm going to say V equals V divided by max abs V. Okay, let her go. There we go. So it looks like we're converging to around 6. I don't know. It's too fun not to do this. Ooh, wow, I didn't even know that could happen. So you learn something new every day. So it's probably converging to 6, and you're probably getting this crazy round off error. Anyway, that was fun. All right, so you can use Aitkens to speed that up if you like. But I'm not going to ask you to do that. Just have fun with the homework, enjoy this, play around with this, and let me know if you have any questions. Okay? I will see you around.